if you go to either announcements, I posted an announcement. So first of all, whenever I post an announcement, you should get an email. Is that right? Are you getting emails? If you don't, you need to fix that. Okay, that's important. So I posted as an announcement. I also put it in modules. So 2 different places, the office hour schedule. So in modules, it's the very first thing. And the deal with this is that I teach 2 lectures of this. And so between the 2 lectures, I have 3 TAs. You can get help from anybody at any of these times, not just Zach and Pollock, okay, or not just your TA and me. So here's the schedule You can go to any of these hours, and these are all people that are familiar with our curriculum. If you haven't noticed, it's different, right? So what we're doing is different than maybe this is called what's called Dirac calculus. Dirac calculus, and all these people are experiencing Dirac calculus. So you've got myself, I'm on Mondays and Tuesdays, Zach, Pollock, Matt, the yellow, he's the afternoon lecture TA, so he's good. And then all these other ones down here, Tuesday through Thursday, Simon, Megan, Sabrina, they're all undergrads who have taken these courses before, and they've tutored before. So they've been tutoring like all last year in the 116. So anywhere it says 116, that's Wexler, the tutoring center, right here. Go out the doors, take a right, or go forward a little bit, take a right. It's over there by there's a snack bar over there. That's right where that is. So anytime it says 116, that's Wexler 116. And then I'm in ECA 209. And then Sabrina here, late on Tuesday, Thursdays, she's in HAV F101. And like I said, these are the people you want to seek out for help because they all are familiar with what we're doing in this class. Okay, they have experience with that, and that's the help you want. All right, so look at all these opportunities for you to get help. Okay, and most of you will need help outside of class, so that's why we're providing you all this support because we know it's different, we know it's harder, so you have to take advantage of this. Okay, there's only a small minority can probably make it through the class and succeed without extra help. Okay, so that's why we're offering all this. Please find us. Find the people that you like and see them regularly, okay? Any questions on that? So that's an announcement and the first thing in modules, in case you ever forget that schedule is there. Any questions? Okay, well, let's just jump right in. Hopefully you can see your notebooks well enough. But so I don't have a worksheet for you today, but so you're going to want to take good notes. And as you know, so good notes doesn't mean copying down what I put up there, right? So it's like you got to really listen and synthesize it, and abbreviate, figure out what's important, what's not. So when you look at it later, you really can remember. Another thing with the class videos, when you go back and watch the video, that's a good time to take a good set of notes. Like you can pause the video and recreate a good set of notes. And that's a really good way to learn and reinforce it. Okay, so what are we doing? You know how fast something is changing at every moment. What's that? You know how fast something is changing at every moment. Exact rate of change function, right? Exact rate of change function. We've been working on this flag lowering example the whole first week. So this is exact rate of change function. All right. And what did we do? We said that it's really hard to find accumulation of height if the rate of change is changing, right? If the rate of change is changing. So what was our next step then to make progress towards exact accumulation if we have a changing rate function? What's that? Make a pretend rate function, right? And so we had 2 different ways of doing that. Like there was like an eyeball average method, and then we used the left-hand method last time. I think in your homework due Wednesday, it says make a rate function that's trying to mimic the real rate function. So what would that be? Would that be eyeball average, or would that be left? Create a pretend rate function that tries to mimic the actual rate function. That's the eyeball average method, right? I mean, they both do. They both do. But if you're trying to do your best in every interval to mimic the rate, then you're using the eyeball average method. Okay? Okay, but in the end, they both get us to the same place, right? In the end, any pretend rate function made up of constant rates, in the end, we'll get to the same place. Okay, so we started with these intervals of 0.35. So let's turn on the. So this is the one we did last time. We used the left method, and this was for intervals of 0.35. And then when we did that, we saw that our accumulation function looked like this. Now we're summing up these changes in height, right, and accumulating them, and then we've got this function that like kind of records what happens, right, accumulating the changes in height as we go. Okay, so is that an approximate or exact accumulation function? Approximate. It's based on the blue step function, right? So it's approximate. So then we said, so this is not too good, right? Because we've got, our rate function isn't doing a great job reproducing the actual rate function. So we said, how do we make it better? What do we do?
You reduce step size, the increments.
Yeah, we're going to make the intervals smaller. So like, for instance, here's a smaller interval, and then going back to the one we had before. So then now I've got smaller intervals. I held so that was the original one. And so now this new approximate accumulation function is better, right? Is better. And so, but we don't want just better, we want exact. So how are we going to get exact? Just keep making them smaller until
You can't distinguish.
Yeah, you can't distinguish between approximations, right? So if you're at the point where if you make the intervals even smaller, you don't really get anything new anymore, right? So that's the. Here's the on the left. Here's approximate rate function for intervals of size 0.005. And what do you notice about that? It looks, if you blur your eyes, if you kind of squint your eyes, it doesn't look any different than the exact rate function we started with, right? But it's still based on constant rates over very, very small intervals, right? And we said, now, if we were to make the intervals any smaller, this approximate rate function isn't going to really change anymore. And so then we call it a day, and we say, okay, we've landed on the exact accumulation function over there, the thicker one, right? The one that's emerging right now. Okay, so let's kind of write down. What do we start with? We know how fast something is changing at every moment. What's that? R sub h. You know how fast something is changing at every moment, okay? And so I didn't give you what that was, okay? And then what we do? We made the pretend rate function, which we just called R, right? So this is. And that's what the pretend rate function was a step function, made of constant rates, step function. Right? And then from the pretend rate function, we came up with what came next from there. Yeah, so and what kind of, was it exact or approximate? From the step function. Approximate, right? And remember we figured out that approximate rate function, the reason that we did the pretend rate function was we got constant rates of change. And with constant rate of change, we can actually calculate small variations in accumulation. How? Constant rate of change. How can we? What's that? MDX, right? dy is a little bit of accumulation. That's what a dy is, and each one is an MDX. So we took the pretend rate function, right? And we just added up a bunch of those, right? This is MDX, right? And we added up a bunch of those. But then we also said that there was like a little bit more in between in between endpoints of the intervals. We call that the rate of the current interval. And then it's not a full width interval, right? Because that dx is varying through the current interval. So all this is now is just adding up the m change, m variation in x, m times variation in x, plus m times variation in x, to track or record what all the net accumulation in height was. Okay? And so then, what do? We let delta x get really small. Small enough that there's no difference in our approximations, capital A, anymore. And that's our exact net accumulation, or A sub h, right? So exact rate of change, R sub h, exact accumulation, A sub h. So now, when we're small enough, we have a more succinct notation than this thing. We don't really use this. This is kind of just more like the theory of behind the accumulation function, summing up all the little bits of variation. But when delta x gets really small, then those completed intervals are like so small that it's like there's no difference between the size of the intervals, right? This was supposed to be smaller than this, but these are now so small, there's no difference. So this last little partial interval basically becomes the last completed interval. And so we're basically, when delta x is really small, we're just left with this, but then we have a different notation, right? We still sum, but now we're summing up like infinitesimal changes. So that sum is, instead of Greek sigma, is German s sum. And it's like every single value of the rate function. So now we're back to the exact rate function, because we're going to pick every single value of the rate function times an infinitesimal change in x. And that's starting from the net accumulation since A and to x. But we need something different here. Because x stands for where we've accumulated to. And for every one of those values where we've accumulated to, we have to track all the x values in between from A to that x value. So we need a different variable there. So we'll say t. Yeah, please. Yes, please.
What lights specifically?
Just I want the lights on in the classroom, but not those. Yeah. Thanks. Okay, so this is when our intervals are super small. These are essentially the same. This is the approximate accumulation function. And this is just the way that we express the exact net accumulation. And this is integral, right? So this is where we're heading, integral. Okay. So this is when we'll talk more about that. Okay, so this is what? This is net accumulation, or in our example, it was how much variation since 0.6 seconds. That was the example we looked at. So now what if I want the height of the flag? What if I actually want the height of the flag? Because that's the height of the flag is how much of it you have at every moment, right? So you know how fast something is changing every moment. You want to know how much of it you have at every moment. So that's actually the height of the flag. Okay, so how do I get the height of the flag function from the net accumulation function? I didn't see any lights on there, so volume, but no lights.
Yeah, so I tried the switches, and
We did too.
yeah, so since now we're not working, that's not really something that we can do, but we can put on the request.
Okay.
And ask them.
I didn't know that. I just didn't. So it's those switches, or just something's wrong with it?
Probably.
Okay. All right. Thank you. Okay. So I've got the net accumulation function here, and now I want the actual height function. What do I need to do to get the height function? So there's this h, right? So this. What we want now is from here is h of x. Where's that going to come from? We're so close, right? We're so close. How do we get the height function from our exact net accumulation function now? Does anyone see what we need to do? So if we have a function that tracks changes in height, how are we going to turn that into a function that actually gives us the height? That's what I'm saying. Yes, sir? No, because the integral is giving us, the dependent variable, the integral is giving us variations in height, like how much it's changed since 0.6 seconds. So at 0.6 seconds, that function gives us 0. Right here, right? It gives us 0. But we want a new function that at 0.6 seconds gives us the height of the flag at 0.6 seconds, and then subsequently all the other times too. Yes, sir? No, not quite. I think maybe you're thinking that the rate is constant. We got a changing rate. Yes, sir.
Would be the initial height of the flag plus a sub h of x.
So when you say initial height, what do you mean?
Where it's like the actual structure height of the flag,
The starting height of the flag? You're onto it. What?
The height of the flag at 0.6 seconds.
Yeah. Yes. Right. Yeah. So if we knew the height of the flag at 0.6 seconds, then how would we get all the heights then? What would we do? Yeah. No, that's what this is. But that's not accumulation. This function gives us changes in height since 0.6 seconds. So at 0.6 seconds, that function is 0. Do you understand? This doesn't give us the height of the flag. It gives us how much the height has varied since 0.6 seconds. That's this bold function down here. So now I want the height of the flag. So meaning at 0.6 seconds, I need a new function that gives me the actual height, whatever that is. Maybe it's like, up here. And then from there, gives me the height at any x. So someone's, yeah.
Would it be h of 0.6 plus a sub h of x?
Right, so what we need is, we just need that start, we need the height at 0.6 seconds. And what is the height at 0.6 seconds? He said it. H of 0.6. And then, for future x values, we just need to what? Add on how much variation you had, right? And what's that? A sub h, or the integral. So we did all, this is super important, we did all this work, we've spent a week coming up with this. So now this is the key to getting the height function, or the how much you have to use it, right? And how do you use it? Well, you've got the changes, so you just need the initial value. You just need how much of that stuff you had at whatever your a value is. So this isn't a anymore, this is 0.6. Right, so this, so then what's that going to look like? So here's the height at 0.6, and then if I add on the variation and changes, what will the graph look like? It'll look just like that one below, but up higher. And then now we're actually, these y values are now actually the height of the flag. Does it make sense? Okay, so this is the net accumulation function. This is total accumulation. Or we finally arrived, how much you have at every moment. How much you have at every moment. So what if I knew the height at 0? That's more realistic, like the height of the flagpole. So I could also write this as what's probably more convenient would be, let's start with the actual height at 0 seconds, like the height of the flagpole. And how would we write the height function now? So we got the height plus. Now what's different now? Now I need net accumulation since 0, right? So now I need to track variation since 0. And we need a different, so the t is x, but it's not this x, right? This x is net accumulation out to x, for each one of those x's, we need to track all the x values from a to x. That's why I need a different variable there, and I call it t. So this is still the x variable, still the x quantity, but we need a different variable. Okay, doesn't make sense. So this is a summary of the journey, right? You know how fast something is changing at every moment. You want to know how much you have at every moment. Rate of change of height to height. But notice, if I have r sub h, I don't have to do this. I don't have to do all this middleman stuff. You know, it's kind of like we did the heavy labor. We put in our time. If you have this, now you can just write this. You don't have to reinvent the wheel every time. You just take the rate function and what? You just write it there, and you have the exact accumulation function. But now we know where that came from, right? So now we know, where does this net accumulation, this integral function, it comes from the approximate accumulation function, which consists of summing up those little bits of variation for the constant rates from our pretend function. Okay. So let's summarize here. Principle 1, constant rate of change. 60 miles an hour means for any given change in time or any variation in time, the variation in distance is 60 times that change in time. And so why is it important that we have to say this rather than, oh, every hour you go 60 miles? Why is it important? Yeah. And for our purposes, what do we want that? What is that change eventually going to be? For our purposes. Small, right? Way smaller than 1, right? So it's not just that there's 60 miles every 1 hour. We need to know like how many miles every little bit of an hour, right? That's where we're going in this journey. We need to make those variations in the independent variable small. Not just 1. Not just 1. Okay? All right, so we said net accumulation function gives the amount of change and the amount of variation in the quantity for any value of x when the rate of change is known. Most rate functions are changing rate functions. Often realistic ones are changing rate. Okay? This is great. You can't write all this down. So pretend rate function, right? We mimic the rate function with constant rates and add up the changes to estimate the net accumulated change. And this was our approximate net accumulation function for a pretend rate function with steps. And at the heart of it is our constant rate of change. M times change in x, m times change in x. We're just accumulating them, right? Accumulating, adding up the little changes, m times change in x. Okay? We said that a better pretend rate function meant a better net accumulation function. Better ingredients. Better pizza. Papa John's. They're not paying me. Okay, so we said if you make the small interval smaller, you get a better rate function and you get a better net accumulation function. So then to get exact, we want super small intervals, right? Super small intervals. Exact net accumulation is found when the approximate accumulation functions are no longer distinct from each other. So our approximate net accumulation function, there it is. As delta x goes to 0, see that? What happens to the little partial interval? When everything is small, it becomes like the last complete interval. So it goes away. And then our exact net accumulation function has this new notation, right? Different notation because the intervals are so small now they're adding together. It's kind of like a little bit different. So because they're so small and there's so many of them, we have this different notation, integral notation. And that's our exact net accumulation function. Okay, and then the last principle, this is principle number 7, exact total accumulation. We're going to add any previously accumulated amount to the net accumulation to get a total accumulation. And this is it, how much you have at every moment. And so all the previous accumulated amount or an initial amount is the value of the function at our starting point for the net accumulation. So whatever f of a is everything you've accumulated from before in a lump sum. And now we're going to add on the changes from there, and this is going to give us the how much you have. Anybody have a question? Okay, so let's. Yeah, so you again the video. If you for the notes, if you want to get good notes, it's the video. Please, thank you.
Is there a reason why our variable changed from H to F?
Now H standard for height, so that was like height of the flag. So now this is generic, any quantity, right? So this is any quantity's rate of change function, and then that amount of that quantity. Yeah, so F is generic for could mean anything now, and I was using H for height. Yeah.
So the T, that's just because it's very small interval, so it's gonna.
It's because so X is some value that we've accumulated to.
Okay.
In order to do that, we need to accumulate all the little bits along the way. So we need a different variable that's varying from A to X and tracking the rate function and adding up the bits to get to X. Because if I put X here, then all I would be doing is taking the single rate at the end and applying it for all of the values, like a constant rate. But I need something else that varies and gets all the different rates until X. Does it help? Mm-hmm. Okay. All right, so here's so we're going to think of this, right, our exact net accumulation function as this, as the approximate net accumulation function with a small enough value of delta x so that the very small size of the completed intervals makes the partial interval essentially the last completed interval. So that partial interval kind of gets absorbed into the sum of the rest of them because they're all so small. So it goes away. And so now we're going to ask, how are they the same? So this is where you're going to practice. How are these two notations the same? How do we get the exact net accumulation function from the approximate? So here's a series of questions. So you're going to go through each of 1 through 4, and you're going to identify that thing in both expressions, right? So we know how fast something is changing. So you're going to identify that in Exhibit A, and you're going to identify that in Exhibit B. And then you go on to number 2. We want to know how much of it we have. You identify it in Exhibit A, and Exhibit B, and then go on to the next one. So in each one of those 4 cases, you read it, you figure out where do I see that in the first one, and where do I see that again in the second one. You see in the first one, where do we see we know how fast something is changing? R sub f of t, right? Or the exact rate function, right? And where do we see it down here? R sub xj, our pretend rate function, right? So we start with the exact rate function, and then we have the pretend rate function. Okay, so there's that. That's where we see how fast something is changing. Okay, we want to know how much of it we have. Where do we see that in the top one? How much we have? Yeah, AF of x is tracking changes, and then we know we're going to add the initial amount. Okay, what about down below? A of x. Okay, so how much we have is one easy step away from this, which is how much variation since. Okay, which is found by summing up. Where do we see that in the first one? Integral means German S means sum, and then in the second one, sigma, Greek S, sigma. Okay. All right. So here's the most important one, and most of the time students blow this. Where do we see in the first one? Where do we see a bit of variation? Where do we see a bit of variation in the first one? Oh, I've heard like 4 answers now. So people are saying dt. Is that a bit of variation that we're summing up? Nope. R sub f of t. Is that a bit of variation that we're summing up? Nope. What was the heartbeat of this whole thing? Remember? No, but I'm asking about a bit of variation. I'm asking, we're summing up many bits of variation. So where do we see a bit of variation? Remember I said this is the heartbeat of the whole thing. What's that?
Is it product of the rate of change and the change?
Yes, m delta x, m dx. Remember, this is the whole thing, constant rate of change. That's a bit of variation. The rate times a little change in independent gives us a little change in dependent. That's what we're summing up. So before we started the discussion, how many people got that? Not enough, okay? This is the whole key. This is the whole key. What is that? It's a little bit of accumulated variation in our quantity. That's what we're summing up. We're summing up m dx's to track the net accumulation. Okay, so independent variable in both cases is what? Is A the independent variable?
No.
What is A?
It's the net accumulation.
Starting value of our independent variable. Where the value where we're going to start accumulating from is A. So what is the independent variable? X, right? So X. T is another letter to symbolize X. So T is kind of true as well. But X is our independent variable. So for any given value out past A, this function gives us the net variation from A to that X. That's our independent variable, X. Okay? And then what's the dependent variable? The left side of both, right? So the amount of variation in our dependent variable, or the net accumulation. That's our dependent variable. Yeah?
If you were to plug something into the first, something like amplifying 1.6 to like 7,
Right.
and you just put in 7 for x, what would you put for t?
You leave it as t because for that, what did you say? What number?
Like 0.7.
0.7 to 4. Okay. So you're going from 0.7 to 4. We need t to vary from 0.7 to 4 to accumulate all the changes. So t stays t because it represents every x value from 0.7 to 4, accumulating up all the changes, like we've been doing last week. In order to get that amount of accumulation, we need to sum up all the little bits. And that means that we're looking at all x values between 0.7 and 4, and that's what the t does. So it stays t. Does it help? Yeah. The independent variable is, let's go back to the graph. So the independent variable is the current value of x. So you see where the point is on both graphs? That point, its x coordinate is the independent variable. So for any given value of x, our net accumulation function is telling us how much variation we have at that value of x. So if I pause it, independent is independent, and here I am. So independent variable is x. That's x, our independent variable. So, and then y is? This is my y, and this is the dependent variable, is net accumulation of height since 0.6 seconds in this example. So there's my independent and dependent variables at this moment coming together to give us this correspondence of those two. Time and net accumulation of height since 0.6 seconds. Does it help?
So, time must be seen as like
The what?
the balance.
The bounds of the integral will be values of the independent variable. Yeah, so as we go, say from 0.6 to whatever this is, then the value of the integral is we get this much variation. Yeah, sure. Other questions? Okay. So let's practice. So, in Calc 1, you should have seen expressions like this. Maybe now, maybe not, maybe now. Now we have a different view of what this means. So when you see this, in light of our first week of class, what should you think? How do you interpret that? What's the meaning of that? Well, there's a lot packed into it, right? You can't say it in 2 words or 3 words. So if we were to come up with a statement that expressed the meaning of what you're looking at right there, what would it be? Could anyone give it a shot? What is this? Anyone want to try? Yeah, please.
That represents the exact net accumulation function.
Okay.
From 3 to x.
Okay, the exact net accumulation function from 3 to x for a quantity. And what do we know about that quantity?
That it is modeled by the function square root.
The quantity is the square root of t?
No.
So the net accumulation of a quantity as x goes from 3 to x, if that quantity, what? What do we know about that quantity, right? So this has to tell us, looking at that, we know what about the quantity, the most key thing that we need in order to write this. What is radical t? The rate of change of that quantity, right? Yeah. So there's some quantity that this is the net accumulation of starting from 3. And that quantity, what? Has a rate of change of radical x. Okay? So here's another way to say that. So we're not going to just copy and paste the words, same words every time. We're going to practice. So yeah, so when you see it, you think of it as a net accumulation function, right? You think of it as a net accumulation function. And here's one way to say it. This is the exact accumulation of changes in some quantity f due to its variable rate of delta square root of x at every moment t from 3 to x. So it's the net accumulation, right? Exact net accumulation. You can put net in there. Of changes in some quantity f due to its rate of change, variable rate of change, square root of x, at every moment starting from 3 to x. Okay, so now I'm going to give you a couple more to practice on, but you're not going to, you have to do this in your own words. You can't just rewrite that statement and then plug the different values in, okay? I want you to, totally in your own words, try again for these two. Okay? Was there a question? Yeah. Are you sure? Okay. So I'm going to continue on attendance. Again, in your own words. Start from scratch. Like, understand the meaning of that. Think about what that means. And then try to formulate in your own words what these two mean. And then practice back and forth. Refine, like, go back and forth. And as a pair or a group, try to refine and come up with a good explanation of the meaning that you agree on. Okay? Go. What did you say for the meaning of this is stating it just verbatim would be you'd say this. This is the integral from negative 4.8 to x of sine u du. All right, so we can all say that the integral from negative 4.x, negative 4.8 2x of sine u du. And but then what does that mean, Brandon? What do you think?
As it goes to the net changes at the rate of sine of u from the points negative 48 to, oh, is that, yeah, negative from the points negative 48 to
Okay, yeah, that was really good. Just at the end to x. Right, so u takes on every value from negative 4.8 to x. Okay, so did you hear what he said? Pretty good. Okay, let's see here. Spin the wheel. Where's Angel? Angel Hill. All right. How about the next one? In your own words, did you come up with something for this one? Can you try on the fly? So this is the integral from 0 to 12 of w squared minus 7 dw. Right. So that's literally reading it. But we want to see it for meaning. So what would it mean? That's right. Any part of it? Just a little bit? This exact accumulation. Okay. Getting some help from Veronica there? Veronica, you want to do it? Good. Okay, pretty good. Yeah, nice. All right, let me just show you what I wrote for those two, and we'll be done. Let's see where else. Shoot. Okay, so here's another way to say it. This is the exact net change in a function, say f, as u varies from negative 4.8 to x, if the rate of change of f is the sine function.